In this lecture, we are going to start with lecture 5, which is joint probability distributions. In joint probability distributions, we are going to be dealing with at least 2 events or 2 random variables, but actually for the level of this course, we are going to be only concentrating on 2 variables. Where did we see in this series of lectures 2 variables previously? Let's see, we have seen in the chapter related with the probability, introduction to probability, we have seen more than one variable, random one variable, or more than one event in conditional probability and in the independence. Actually, to have conditional probability, we should have at least 2 events. You should condition one event to another. And if we are talking about independence, of course, we are going to be talking about at least 2 events. Then we continue with discrete and continuous random variables. And during and throughout those topics, actually, it was always a single random variable. There was one case on the other hand where we had defined a series of random variables using actually dissecting one random variable, which was a series of Bernoulli trials, and the relation between a series of Bernoulli trials and binomial random variable. If you recall, the sum of the outcomes of the Bernoulli trials is going to be equal to binomial random variable outcome, and each of the Bernoulli random variables may have 0, 1 outcome, and we have shown it with xi, x1, x2, x whatever the number of trial, and we used also capital X to denote binomial random variable. And in that case, we talked about conditions. We talked about questions like what is the probability of the second event conditioned on the first event, and actually we have seen that in Bernoulli trials, each trial, so x2, x3 is independent from all the previous trials. So x2 is independent from x1, x3 is independent x1, x2. So basically during that part we kind of we just touched on joint probability or the concept of joint probability distributions, but we have never talked about that, but we actually touched the topic of more than one variable. Now in this chapter we are going to be rigorously talking about joint probability distributions. Actually, as I said, it's going to be only 2 random variables that we are going to be talking about to come up with a joint probability distribution due to the introductory level of this course. Basically, you should think about joint probability distributions or more than one variable case as the more realistic case compared to a single variable case in most of the topics that we have talked about. Usually in real life, when we have a random experiment, and you may think about this random experiment of any chemical process, for instance, this is a distillation column or something else, of course, there is a highly deterministic element in distillation column, but there is going to be always some fluctuations on the designed or the computed values. And therefore, those fluctuations will form the basis of will be due to the random nature of that experiment. So in that distillation column, maybe distillation column was not a very good example, yet still, as I said, there is always some random component in any chemical process. We are not going to be only dealing with temperature, we are going to be also dealing with other variables, or temperature of one tray, or temperature of another tray, or temperature of some certain top tray, let's say, and pressure of, let's say, of the distillation column. So we are going to be usually in process industries, we are going to be talking about multiple random variables. So we are, as I said, going to be concentrating only when the number is 2. So the resulting probability distribution, if there is more than a single random variable, is called joint probability distribution, and it's shown with this representation. If in now in subscript capital X and Y, and in parentheses lowercase x and y, representing the values of taken by the random variables X and Y. Note that unlike the case where we have a single random variable, recall that we actually just dropped this X for many cases, capital X, and we have shown it in this way because there was only one random variable. Here we have now two random variables, and the order of those random variables are important to denote or to show which of these values correspond to which of those variables. Therefore, we are going to be using the subscript notation here. So for discrete, if X and Y are discrete random variables, well, the typical example, let's say it's going to rain tomorrow or it's not going to rain tomorrow. That is one random variable with 0 and 1. And Y maybe I'm going to wear a jacket, for instance, 0. I'm going to take an umbrella, but not wear a jacket or something like that. Also, you may talk about all these different outcomes or different values that the random variable may take. So the question or the joint probability mass function in this case will be something like the probability that it's going to rain and the probability that I'm going to be taking an umbrella. That Y is going to be equal to taking an umbrella or not, and it's going to rain or not. So what is the probability that it's going to rain and I'm going to take an umbrella? What's the probability that it's going to rain but I'm not going to take an umbrella, or any scenario that you like? So in this case, when you have two discrete random variables, what we call joint probability mass function. Note that this probability distribution is going to be denoted with a probability mass function because we are talking about discrete random variables. So we have masses at certain discrete values of X and Y. Now again, just like the what we are going to call marginal distributions of X. So I'm going to give that the definition of marginal distribution in a couple of slides later. But just keep that in mind. This distribution is actually Fx, and what we call Fy are marginal distribution of X and marginal distribution of Y. So just like the marginal distributions of X and Y that we have talked about, each probability mass function at each value of X, so for every X and Y value, this condition should hold. Actually, when it's non-zero, actually when we are on support of X and Y, range of X, this is going to be non-zero. Otherwise, it's going to be 0, but it cannot be negative. As I said previously, because in two variables case, it's the same thing, probability mass function, mass cannot be negative. So just like again for one-dimensional marginal probability mass function case, the summation, but this time over all X and Y values, should be equal to 1. So over support of X and Y, when you sum the probability mass function values, it's going to 1. Recall that this law over all X values. For a single variable case, we had this one, or for over Y, and we are going to be, as I said, calling this marginal distribution of X and Y. These are the conditions that we have covered in chapter 3, if I recall correctly. So the same conditions will also apply here. Now, at this moment, let me also give you another perspective to consider these joint probability distributions. Now, when we use something like this, we probably, in our mind, visualize a probability mass function over a axis, a real axis such as this one. And this is the support of X value, the support of X, the non-zero values of X, non-zero values, the probability values with the probability with non-zero values. All right, so X is going to be an element from X1, X2 to X5. In this case, Fx is not equal to 0, given some certain values. So now when you have, or you may think about this as Y. So this is the probability mass function of X. You can write something like that for in terms of Y. When we are talking about a joint probability mass function, we are going to be talking about in 2 dimensions, or here the support will be in 2 dimensions, just like here the support was 1 dimensional. Now support will be on this area x and y plane, whereas probability mass function here will be shown in this manner. I should now actually also write fxy, x and y. And we are going to be talking about a meshed region. So there's going to be, again, some discrete x values with non-zero probabilities. There are going to be some y values, discrete y values with non-zero probabilities. So for each of these points, as I said, on a mesh, we are going to have a different probability mass function. And actually here, this is exactly what we are talking about. This xy, fxy, is going to be the probability of these each points on that area. And actually the third property gives an idea or summarizes this whole point. The probability mass function of x and y at a specific x and y value is going to be equal to the probability at that point. And here what this says is, if you add these values, it's going to be equal to 1. So that's it. Now, I'm sorry, still not very, how can I erase all of this? I think, yeah. All right. If, on the other hand, x and y are continuous, then what we are going to be talking about is joint probability density function. So it is the very same thing that we have covered in marginal, the distribution functions. If x and y are discrete, we have probability mass function, but what is added here is the word joint. So we are going to have the joint probability density function if x and y are continuous. The very same thing, the first condition is identical here for all values of xy. Here, just like over the support of for all values of xy here, we are going to have a non-negative probability mass function value. We're going to have a non-negative probability density function value. Now, just like the relation between one-dimensional discrete distributions and one-dimensional continuous distributions, now the summation turns into an integral. But now, since we have 2 variables, 2 random variables, this is going to turn into a double integral. Hence, let's also show this graphically. If we are talking about a single dimension here, the probability is going to be found by finding the area here between A and B beneath this probability density function. So it's going to be fx dx single integral. When we are talking about 2-dimensional probability density, or probability density above a 2-dimensional area, is going to be x here and y is going to be here. We are going to be above this region, so above this area there's going to be a surface, and beneath this surface we are going to be finding the volume. So it's going to be a double integral fxy dx dy above that region we are going to call R, for which we would like to find the probability. And if this range is the support of x and y, in other words, from -infinity to +infinity over all possible values of x and y, note that the outside the support of x and y is going to be 0 probability density. So these are the limits of integration, whether it's from -infinity to +infinity or between or within the support of x, is the same thing. This is going to be equal to 1. However, if you just do this integration above a certain region, just like this one, then the resulting integral will be the probability of x and y being within that region. So when you find the probability here, actually, or the volume here, what you are actually finding is what is the probability that x and y values are within that region. This is exactly what you are finding, and this is exactly the same thing here, because here actually for 1 dimension we are actually finding what is the probabilities x belongs to that region, where x here denotes the range A and B. So what's the probability that X is between A and B? What's the probability that X and Y belongs to that region? And this region now consists of a two-dimensional area. All right, it's a very simple question. Let's solve this. X and Y are continuous here. Actually, this representation already shows that. Nevertheless, I have added here. And let's say that probability density function of X and Y is given by this equation. So it's going to be equal to, everywhere it's going to be equal to 1/6. Prove that fxy is indeed a joint probability density function. Here it should have joint probability density function. Note that it's not mass, it is density because X and Y are continuous. Well, as I said previously about the one-dimensional case, probability mass functions and especially probability density functions, it is a good idea if you can very easily to draw a diagram or to draw to show the probability density function in graphical form. And in two dimensions, I think it's even much more important, but it may be slightly more difficult to show, of course, in two-dimensional regions. So actually, I just draw a diagram or a graph of that or using MATLAB. So what we have here is X is between 0 and 2, so it is this region. And Y is between 1 here, 1 and 4. And overall X and Y region, we have a constant probability density function. This is fxy. Everywhere it is 1/6. So the question is, prove that fxy is indeed a joint probability density function. Now, two conditions we need to consider. First, fxy should be greater or equal to 0 for all values of X and Y, which is the case. Actually, outside this region is all 0, and inside this region, 0 X is between 0 and 2, and Y is equal to between 1 and 4. We have probability density function equal to 1/6. So this condition is satisfied. Now the second condition is the summation or integral of this probability density or mass function, and here we are talking about probability density function. Therefore, it's going to be an integral of probability density function dx dy over minus infinity plus infinity is going to be equal to 1. Now we are given actually the support of X and Y very clearly, so let's use them. Let's first write for X, it's going to be 0 to 2, so it's going to be Y is going to be from 1 to Y, and probability density function is given as 1/6, and we have dy and dx, and this is going to be equal, this should be equal to 1. Let's a question mark here. So the next step is going to be equal to 1/6. This is going to be very simply 4 minus 1 multiplied by 2 minus 0. And if you do the calculation, it's going to be, let's see, this is 3 and this is 2, and yeah, they cancel, and it's going to be equal to 1. Actually, you don't need to take this integration. It's very obvious that the volume of this cube is not that it's going to be equal to the volume of this cube is going to be equal to 2 times 3 times. So it's going to be 2 times 3 times, and this side is going to be equal to 1/6. So equal to 1. Again, what we are finding is actually the volume under this region. But for more complicated regions, you should realize that we should, of course, take this integral. What is the probability that X is going to be smaller than 1 and Y is going to be greater than 1? So let me again get rid of these things. So what we are talking about is this region. X is going to be smaller than 1. So this is X is 1. All right, and Y is greater than 1.5. So if this is 1, I think this is 1.5, something like that. Let's call this 1.1. Let me do it again. All right, that's as good as it gets. y greater than 1.5 and x smaller than 1 is, I guess, this region. Y smaller than 1, I'm sorry, x smaller than 1 and y greater than 1.5. All right, so what is asked is actually the volume here. Volume of this rectangular prism is asked actually. Again, you can directly find the value here because it's the whole thing is rectangular, so finding the volume is very straightforward. But note that this is equal to the volume of that rectangle. I want you to have a geometric understanding, but again, let's use the integral form. So it's going to be equal to from 1.5 to 4, and from 0 to 1 it's going to be 1.6, and this is the x dy because these are the limits of x and these are the limits of y. I hope I'm doing it correctly. It's going to be equal to 4 minus 1.5 and 1 minus 0, so it's going to be 2.5 over 6. This is going to be equal to 470. Of course, it should be smaller than 1. All right, now let's continue with marginal probability distributions. As I have already introduced what marginal probability distribution is. How to find this, I'm going to talk about right now. But individual distribution of a random variable in a multivariable process is called marginal probability distribution. Now let's make this straight. Actually, in chapter 2 and in chapter 3, in chapter 4, we have actually covered marginal probability mass function of discrete random variables and marginal probability density function of continuous variables. So we have already covered marginal probability density and the mass functions. But we have only, since we already concentrated on a single variable, we didn't give the name marginal, and probably we could have thought what else could there be. But now that you should realize that in multivariate processes, and note that multivariate processes is the typical nature of processes in real life experiments. So usually most of the processes in real life, especially in engineering, are considered as multivariable processes. So although you only regard a single variable without maybe paying much attention or without thinking about it much, you are already dealing with the marginal probability distribution because you concentrate on a single variable, but there are you actually realize, or maybe you don't realize, but there are probably many other random variables around. So directly, indirectly, there are going to be dependencies between those, but you just forget about them. You just concentrate the distribution of a single random variable, and this is something that we have covered. Now what we are going to see is the relation between joint and marginal probability density functions or probability mass functions for discrete random variables. So therefore, we are talking about probability mass functions. Marginal probability mass function of x is going to be joint probability density function is taken, and it is summed over all values of y. So the idea is very simple. If y can be equal to, for instance, 0 and 1 and 2, then the marginal probability density function of x, which means I do not care about what the value of y is going to be equal to y xy x y is equal to 0 plus xy x y is equal to 1 plus xy x y is equal to 2. When you add those two, the rationale is you cover all the possible values of y. Therefore, at the end, the resulting function is not going to be a function of y anymore because you considered all the probability mass functions values of y. So, well, the same logic applies if you would like to obtain a marginal probability mass function of y. This time you should add the joint probability mass function over all values of over the support of x, over all values of x with non-zero probability. Now, when it comes to continuous random variables, therefore we are going to be talking about probability density function. It's the very same thing, but summation sign turns into an integral. So if you would like to find the marginal probability density function of x, what you do is you take the joint probability density function. Note that this is going to be density function because we are going to be talking about continuous random variables, and you integrate over y, right? Over the range or support of y, over the values with non-zero probabilities. When you do that, maybe it's easier to understand the concept here. When you do this integration, note that all of the y values will be replaced by the range of the, probability of the corresponding joint probability density function over those y values. So the resulting function is not going to depend on y anymore, because we have exhausted all the possibilities of y. So the very same thing for probability density function of y. Then you have to sum over all values or over the range of x values. All right. Now a simple example. Let's see. Now x is equal to 1, 2, and 3. Actually, maybe I should have shown that in curly brackets. When they are curly brackets, these are discrete random variables. When it is like this, then it's going to be a continuous random variable between 1 and 2. So I think even a better representation would be this. So x belongs to this finite set and y belongs to that finite set. And the probability, now we know that since x and y are discrete, this is a probability mass function, is given by this equation, and c is not known here. And the question is, what is the probability that in such a system x is going to be equal to 1? So now let's try to visualize this problem in an empirical form. What does this correspond to in reality? If you just leave everything to mathematics, it may be a little bit abstract, especially for us chemical engineers. So there is a process here, and let this be something like concentration at 3 different values, and this is a concentration of another substance, another solvent, let's say, and this may be all these, again, these discrete values. And there is a certain probability mass function resulting from those values. As the concentration values of x and y are higher, 3 and 4, actually the probability of obtaining that product is also higher. That's what it means. Maybe we just mix these two, so therefore we just add those concentration values. I don't know whether that makes sense physically, but I think we can empirically visualize something like this. What we don't know now, the mathematical problem, is the c value here, which we can easily find. And what the question asks is, from such a process, if the probability mass function is associated with that, represented by that equation, which means that the lower concentration values are less probable compared to higher concentration values, then what is the probability that when I take a sample of x and y together or separately, what is the probability that x is going to be equal to 1? Note that although this is a process consisting of 2 variables, consisting of a joint variable case, this means I don't care about what the value of y, it may be anything. I just care about the cases for which x is equal to 1. Or in other words, note that this is equal to, x is equal to 1, y is equal to 1, plus x is equal to 1, y is equal to 2, plus probability x is equal to 1, y is equal to 4. Actually, this was just maybe heuristics, but actually I have already used this equation. I take the probability mass function, joint probability mass function value, I add over all values, all the possible values of y. So this is going to be, as I said, heuristics, but also we are using this equation here. But before that, let's solve first this part to find c. So what is the, well, first the condition is c is going to be greater equals 0, because since all the values of x and y are positive, this should be also positive, so that, or non-negative, so that to make this probability mass function greater or equals 0 for all values of x and y. Anyway, so the first part. But we can find an exact value. How? We should remember that if we sum over support of x and y, x, y value, this is going to be equal to 1. So that's exactly what we are going to do. When we equate this to 1, there's going to be only one unknown from this equation, and we can find c value. All right, let's do it. So here is the idea, cx plus y. Now, these summation things may be a little bit tricky, so this is going to be, let's say that first sum with respect to x, then sum with respect to y. Now, you can write each of these values and sum it, but we have more practical ways. If you are a little bit if you get a little bit used to that, those operations with summation sign is going to be very handy. So here is the thing, we can write this as cx plus cy. Well, actually note that this means here there is a parenthesis. I think this is also pretty much obvious. Well, you can take, of course, c out. So this is going to be y x x plus, you can take into the common parenthesis of c, actually is going to be, I think, easier. And this is y x y. Okay, now there's a little bit of arithmetic here. We can change the order of these summation signs. This is something probably you know from some mathematics course, but I don't know how much you apply it. Okay, so now also let's try to deal with this part. This means that over the range of x, add each value of x one by one. Hence, this means actually, where are the x values? Actually, let me write that x is element of 1, 2, and 3. X is equal to 1 plus 2 plus 3, which is going to be equal to 6. So therefore, this is going to be y6 plus, this time we have x here, and we can do the same thing for y. It's going to be y is a member of 1, 2, 3, 4. It's going to be 1 plus 2 plus 3 plus 4, which is going to be, is it going to be 10? Yeah. So this is going to be equal to 10. Now, what about this one? This one, these ones, as you can see, are constant numbers. So basically what we do here is that whatever the number of values, the size of the set of y is equal to, so y is going to be here consisting of 4 terms here. Therefore, this is going to be equal to, we are going to be adding 6 by 4 times, which means multiplication 4 times. So it's the very same thing here. X consists of 3 terms here, right? So we are going to be multiplying 3 by 10. We add 10 by 3 times. So this is going to be equal to 13. This is going to be equal to 24. And if we add them, what's going to be the result? I should copy here. I'm sorry, this is not. What kind of a multiplication is this? Yeah, that's better. This is going to be 54, and c is going to be equal to 1 over 54. All right. So let's write the probability mass function. Clearly, probability mass function of this process is going to be equal to 1 over 54 x plus y with the domains of the random variables represented. So this is going to be the description of our process. Note that if you recall, a random experiment is described by a probability density or probability mass function and its support. Now we have 2 variables, therefore this is going to be the description. There should be a second part of this. Oh yeah, I have forgotten the solving this part of the question. I have just actually only found this. Maybe I should erase this part so that there is some space left. Otherwise, it's going to be a little bit difficult to handle. Let me, yeah, that's better. All right. So let me write the whole thing again. This is going to be equal to, what was the value? 1 over 15 x plus y with the x and y values given here. So now the probability mass function fx is equal to 1 is going to be equal to, this is xy, x and y. This is sum over y values here. So y is an element of 1, 2, and 3, and 4. fxy 1 over 54 x plus y. This is not that this is going to be the marginal probability mass function. Marginal probability mass function of x. This is exactly what I would like, because once I obtain this, I'm going to just put 1 here and I'm going to find the result. So it's going to be 1 over 15 x plus y over y values and y values. Now again, this is going to be equal to adding the same, adding the x values here with respect to y values. Note that this is actually x is unknown here because it's not an addition over x. So it's going to be, and the resulting thing is going to be a function of x. Therefore, we are going to be adding the x value for 4 times. So it's going to be 4x. And this one is going to be equal to, again, 1 plus 2, 4, which is going to be 10. So the result is going to be 1 over 54, 4x plus 10. This is going to be our joint probability, marginal probability mass function of x. Actually, to make it maybe a little bit nicer, we can write it like 2x plus 5. Note that I'm going to leave it to you, but let me write it. Prove that over all x values is going to be equal to 1. So this is going to be an, you just put the summation sign here. So over all values of 1 to 3, if you sum them, they're going to be equal to 1. So what we need here is, let's finally solve this question. It's going to be 1 over 25, 2 times 1 plus 5. So it's going to be 7 over 25. All right. Now, so this general procedure will be identical to what we have done previously. First, this time we had 2 random variables. We have found we have defined something called joint probability mass and density function, and we related joint probability density and mass function to the univariate cases, and we called the probability density or mass function for univariate cases as marginal density and mass functions. Now we define the conditional probability distribution. So it's going to be nothing new, but it's going to be in terms of distributions. Prior to in the second chapter related to probability, we have defined what conditional probabilities. But we didn't talk about, we defined them in terms of events and events at single probabilities, and we have defined the probability of event A and B. So these were, as I said, events, not random variables. So we defined the probability, conditional probability in this fashion. And note that these are discrete probabilities of discrete events. Now, can we do the same thing for distributions? When it comes to discrete random variables, these are already, the probabilities are equal to probability mass functions, so there's going to be nothing new under the sun. It's going to be just, if we are talking about a probability mass function here of, let's say, x and y, this is the probability mass function of x and y. If you divide by the marginal probability mass function of y, what you end up will be probability max function of x and y in this fashion. I'm very sorry, there is no y here, x here. So again, let's recall the other definition. Probability of x given y is equal to, right? Take these as events for the time being, right? There's going to be some slight abuse of notation, but that's not the big deal. Probability of x and y divided by probability of y. I'm talking about the discrete case. In this case, probability of y is basically going to be equal to marginal probability of lowercase y evaluated for the lowercase y evaluated for, in the marginal probability mass function. And probability of x and y is actually probability mass function, joint probability mass function, evaluated at point x and y. And how do I obtain this? If you go back here, it is basically here. So when it comes to discrete random variables, there is nothing new under the sun. It is just the very same thing. So the resulting thing is going to be what were equal to probability of x given y is basically the conditional probability distribution of x given certain value of y. Now note that there is actually, let me make this clear, this is a lowercase y, this is a capital X, and this is again lowercase x, because here y is given at a specific value. So, and that specific value is lowercase y. You can also show it in this fashion. In this case, I think the logic is more easier to understand. What is the probability of, or a probability mass function of the random variable of x for the given value of y? And this is going to be only a function of x. Note that there is no y here because the random variable is y at a given lowercase y value. Therefore, the resulting function will only be a function of x. And this is the very same thing that we have here. So there is, as I said, there is nothing new when it comes to probability mass functions. Now, when it comes to continuous case, this is the same formulation, but this is something new. Again, the very same formulation, but we are right now using probability density functions. Probability density function, joint probability density function of xi divided by joint marginal probability density function of fy. This is somewhat different. Maybe it looks the same, but somewhat different compared to the original definition of conditional probability, because the original definition talked about probability of A intersection B divided by probability of B to write this expression. Now note that this here is probability, whereas this one is not probability. This is probability density function. When you integrate it with respect to some region, it turns into probability. So therefore, this is probability density function divided by the probability density function here is going to be equal to, again, probability density function of x given y. Again, using the same logic, capital X, lowercase y, lowercase y. So the arithmetics is totally the same, but note that the meaning is now the conditional probability density is found here, whereas for the discrete case, we have probability mass, conditional probability mass function, which is exactly equal to the definition we have. I try to give in chapter 2. So properties of the probability density, conditional probability or probability mass function. Note that this resulting entity is another probability distribution function, and it can be mass or density. Hence, it should obey all the rules related with probability. And again, it actually obeys the rules. First of all, it is a non-zero, non-negative value. It takes a non-negative value over all range of y values. Note that again, given x, this is the probability, the conditional probability density or mass function of y. Now, if we have here y to be discrete, then this condition should hold. If y is a continuous value, this condition should hold. I'm sorry, there should be 1 here. So this is obvious. And again, the probability, what's the meaning of that mathematical integration or summation in terms of probability? When x is given a specific value, what's the probability of y being an element of B? You sum the corresponding probability values with respect to the y values here. Y is going to be actually an element of B, and y is going to be an element of B here, or you integrate it if y is continuous. I think this is also pretty much straightforward. So we have, when you have joint distributions, now we have three entities, starting from maybe a joint probability density function. Let's think about the continuous case. You may, by integrating over the other variable, you end up with the marginal distribution functions, marginal density function. And given some value of the other variable, you can come up with a conditional probability density functions also. And these three joint, marginal, and conditional density and mass functions should obey all the properties of probability distribution functions. And now, since we have three distributions, we are going to, now for the, I'm going to talk about the why we don't have three different expectation and variance operators. We are going to have two types of expectation and variance operators. So let me write the distributions again here: joint, marginal, conditional. Now let me talk about the conditional case here, and then I'm going to talk about why we don't have a corresponding expected value for joint distribution. Now, conditional expectation means it comes from conditional distribution function. Given the x value, given that it's going to rain tomorrow, what do you expect? What's the expected value of the random variable that that person is going to wear a jacket or is going to take an umbrella or not? Or given that it's going to, the temperature of tomorrow's temperature is, let's say, equal to 25 Celsius, what is the probability of, what is the expected value of the rainfall? Or I don't know, let's make it related to chemical engineering. What's given that the current pressure of the, let's say, distillation column is 2.1 atmosphere, what is the expected value of the top tray temperature? So this is conditional mean of y given x is equal to some value. Now the logic is exactly the same. Expected value of any quantity here is going to be found depending on that quantity here, whether it's going to be discrete or not. If it is discrete, we actually write this quantity here. Y is the quantity here. Note that it's not x because x is already given, right? So we are only interested what is going to be the expected value of x. So we weight different values of x, y, with respect to its weight. And its weight now is not the marginal probability density, marginal probability mass function of y. Why is that so? So this is incorrect. Why? Because some information about x is given. When you have no information about x, you use this one. So this is the expected value of y, no information of x. However, if you are given some information of x, then the probability mass function of y actually turns into this one. So actually, given some information on x, the marginal probability mass function of y is converted into a conditional probability mass function of y given x. So therefore, you weight each y value with this new weighting function. And when it comes to the continuous case, it's the very same idea. You integrate with respect to the conditional probability mass function. Density function. Now, when it comes to variance, it's again the very same thing. Instead of this variance, or we know that variance is actually equal to expected value of y minus expected value of x. I am very, very sorry. It's going to be y given x. And this is given value of x squared. Maybe this is a bit of a complicated representation, but it is exactly what we are doing here. We compute the quantity of, and maybe it's a better idea to put square here, and yeah, expected value of this quantity given x. And what is that quantity? Expected value of y given x. Here we subtract the value of all values of y, but again these are still under the condition of that some lowercase x value is obtained at hand. Therefore we use the very same logic here. Y minus, this is expected value of y given x. So this is the quantity we would like to find. We weight this with respect to the corresponding weighting function or probability mass function of y, and therefore it's going to be equal to y given x, y. We either sum this or integrate this. You may again maybe ask this question, why this is the one that we use but not this one is the one that we use. It's because, as I said, there is always that given condition of x is given. Therefore, when this is given, the probability mass function or density function is not going to be equal to the quantity here, but it's going to be the one here.